Hello, Dr. Haluk, and hello, everyone. Uh, I hope you are doing well, Dr. Haluk. And this screencast of my project, Pacman Search, find you well. So this is the project. It is Pacman Search of the game Pacman, which is one of the most popular games in the world. And this project is aimed at designing an intelligent Pacman agent that is able to find an optimal path through each maze, and considering both reaching the corners or reaching the particular locations, and also eating all the dots in a few steps as possible. So, in the implementation of this solution, we will use many algorithms. We will use depth first search and breadth first search, and also uniform cost search, and also ASA. So let's take a look about the content of this project. So we have many files in this zip file. If you download it, you will find those files in this zip. But we will focus on those two files, with search.python and search agents. Here in search.python we'll do the implementation of our algorithms, and here and this file with search agents is where all the search-based agents will reside. So, by the way, this project is written in Python 2, so I downloaded and I upgraded to Python 3. So I was forced to edit all those files to make it able to run using Python 3. So for the questions, we have 8 questions. The first question is finding a fixed food dot using depth first search, and here we have the second question, the same here, finding a fixed food, but here using breadth first search. And also we have here the question 3 is varying the cost function, and the question 4 is do the implementation using a SAR search algorithm. So, and the question 5 is finding all the corners. So we have to know also that this project is separated to two parts. The first part is helping Pacman find path to reach its end goal. The search problem requires implementation of the 4 search strategies, including depth first search and breadth first search, and also uniform cost search and ASA search. Each of which will return a list of actions for Pacman to reach its goal state. And the second part which is start from the fifth question. It is the search problems no longer consists of just one goal position. So now we have to find, for example, all the corners, finding all the corners, or finding the dots, all the dots in the maze by using SR search strategy. Each of these problems must come up with different heuristics or set representation to reflect the nature of the problem, as well to find the shortest path for Pacman. So here the sixth question is the corners problem. It is related to the fifth question, and also here the seventh question we have evening all the dots, and each question is suboptimal search. Unfortunately, I wasn't able to find the solution of all those questions, so I find the solution of 1 and 2 and 3 and 5 and 4 and 6 questions, just 6 questions, the first 6 questions. I wasn't able to find the solution for 7 and 8. So let's start the code. So this is after unzipping, downloading and unzipping the file, the project, we have like we said before, multiple files. So I said that we will focus on 2 files with search and search agents. Search we will implement in search.python. We will implement the algorithms. So let's start with the first algorithm, which is depth first search. So for the implementation, first of all, I create an empty stack using the function stack, and after that, I create also visited list, table of visited list to put all the visited places in this list, and path also the path the agent go from, and also here we have the cost of each movement, which is initialized with 0, and also here we have start position. Here I create pushes the start to position to the stack. I mean letting this start position be a stack. So here we are going to a loop, which will able to detect if the start position or is not empty. So here after that pushes the current position to the visited list if it is not visited, to verify if it is visited or not. Here in this test, it returns the final path if the current position is goal. After that, we will get the successors of the current node, and then in this for loop, which contains a test to verify if the visited the item is not in the visited list. So pushes the current node successor to the stack if they are not visited. So this is the first algorithm. So I will pass to the test. For running the program, there is two ways to run it. But the easiest way is I'm using Visual Code. I run it from here easily. You can also run it using CMD by going to the path of where your project. But I'm going with the easiest way to gain time. So let's start. To run it, I will use these commands. I will put all those commands in the readme.txt. So yeah, that's just this. So as you see, I will repeat it. I think there is a problem because I'm using two monitors. I will repeat it again. So as you see, it is go from this way, and the score is 502, and it is win. So I reach the goal. So let's try with the chini maze, which is the smallest maze. As you see, it reached the goal with 500 in the score. So let's start. Let's test with the medium maze. As you see, it's going from the start, because all we know that depth first search is a uniform search strategy. It expands the deepest node in the current frontier of the search tree. So as you see, it reached the goal with an average of 380. So let's try now with the big maze. Here's the big maze. Should go like that. And also I know that deep depth first search algorithm is a stack follows the LIFO principle. The last generated node is the first one chosen for expansion. As you see, it is also reached the goal. So now I think we should pass to the second algorithm, which is break first search. In the break first search, which is a level by level search, and all the nodes in a particular level are expanded before moving on the next level. Here I start also with creating an empty queue, and also a visited table of visited lists and path, and also action calls initialized by 0, and also a stack. So here we push the start position to the queue. The start position to the queue. Yeah. Now we are going to go in a loop, while loop, and also push the current position to the visited list if it is not visited, and also here returns the final path if the current position is goal. So he will test always if it is a goal, so he is done. If it is not, he will go for the next move. Here we'll get the successors of the current node. We'll put it in successors here by using the method get successors, and here we go. We are going to push the current node successors to the queue if they are not visited, to test if this node is visited or not yet. We check both the visited and also the open list here. If it is now I think it is clear. So I will pass to the test. We are going to test with the medium maze. Here is the medium maze. Like you see, it is different than the depth first search, and it reached the goal of 442. So it is better now. Now it is better than the depth search. We'll go to the big maze now. It is really huge, and this will take a lot of time, and will make the video screencast very long. but I have nothing to do so. So I try to explain very quickly to make the video shorter. So I make all the results in the paper, and also I make, for example, I make I compare it. I compare the algorithm, for example, DFS with BFS and UCS and also ASAP. And I also make I put all the results in the paper. So now I will move to the uniform cost search. Here is the implementation of the uniform cost search. Instead of expanding the shallowest node like breadth first search, expand the node n with the, for example, with the lowest cost path. This is why the frontier. This is why the frontier is sorted as a priority queue ordered by, for example, N or G. So here I create an empty priority queue. Also initialize the priority to 0 and push search position to the priority queue, and go into a loop, while loop, and push and here push the current position to the visited list if it is not visited, like before, and here I return the final path if the current position is a goal. So we have always test if it is a goal or not. So here I guess the successors again, and here I define a function in order to get the priority of an existing node in the open list. So after that, push the current node successors. So push the current node successors to the priority queue. Yeah. So after that, if the successor is already in the open list, we check its priority, and after that updates priority of the successors. If the value of new priority is less, here, if the value of the priority is less, here's the test. If the value of priority is less than that of the old one. So let's move to the test. We'll start with the medium maze. As you see, it is 442, it is like BFS, so it is good. And let's pass to the medium dotted maze. We have dots now. So like you see, he's following the dots. not like before. So as you see, every score is 664. So after that, we will pass to the medium scale image. It is like the same. It looks like same as the dot made. Now I will pass to the ASR search. First of all, I create an empty priority queue, also in like UCS. After that, initializing priority with 0, push to start as before, and now we change our loop and test if this is to show the final path if the current position is a goal. So this is a mask, so I already tested, and pushes the current position. Push the current position to the this place. So to validate that this is already visited and gets the successor of the current node. Now after that, push the current node successors to the priority queue if they are not visited. After that, apply to the priority of the successors using a function fn. As you see here, using the GN, current goes from start stage to the current position, and HN, which is estimate of the lowest goals, using this function heuristic, goes from the current position to the goal state. And we add the G to H to estimate of the lowest cost of the solution path from start state to the goal state passing through the current position. New priority here, which is F, and open this dot push. Okay, so now let's test this algorithm, this implementation. We're just using the big maze. Now, I'm sorry, I didn't copy the link very well. I have problem in copying the link. I'll use Ctrl+C. So that's it. And here is the result using a star algorithm. It looks a little bit slow, but it is better than the other algorithms, UCS and DFS and BFS. So yeah, as you see, Doctor, the time complexity of a star, the time complexity of a star is depends on the heuristic. In the worst case of an in the worst case of an unbounded search space, it will be all be in the power of D, as mentioned in the textbook. So now I think we are done with the four first questions. Now I will pass to the fifth question, which is finding all the corners. This question is implemented not in search.python, it is in search agent. So here is it. This is the function, which is corner problem, and here we are now in the second part of the search problems. We are no longer consist on just end on one goal position, which is finding, for example, the dog. We are now where we should find all the corners or all the dots in the maze. The dots, which means the full piece, by using the same ASR search strategy. Here it is. And this was the most harder part in this project. So I take the challenge and try to fix it. So here we have the code. And now I'm going to test it. Let's go. Problems in the copy in the mouse, so I will repeat it. I'm so sorry about that. And here it is. I'll repeat it. So yeah, we help the Pacman agent to find the shortest path through the maze that touch all the four corners. After that, I will test in the medium maze. It's the same problem. I'm so sorry. Here's the medium maze. Like you see, the Pacman agent is searching for the shortest path through the maze to touch the four corners where the dots. For the question number 6, here's the implementation. It is the corner heuristics heuristic function here. It is a function not trivial and non-negative. I mean by non-negative, it returns 0 at every goal stage and never returns a negative value. And using Manhattan distance function to calculate the distance between the current position and also the corner index. That's it. Now I'm going to test it. We're going first of all to test it in the medium column. And this function is both admissible and consistent, and has been this has been written here in search agents.python. That's all, sir. I hope this screencast. I hope you like it, and I hope my explanation was well. And thank you again for all your effort and all the knowledge you gave us. Thanks, sir.